Number 14, final answer. 2x squared minus 4x plus 3. 2x squared minus 4x plus 3. However, why did they write the answer to the division problem, the answer to, or from up above, and this extra piece? This part comes from setting the bottom equal to 0. And why would we set the bottom equal to 0? What's it called? Find a 0. Why?
Oh, it's because it's the thing in the front because it's x minus 2 and then it's 2.
Yes, that is it.
I don't know what it's called.
It's the 0 to the factor, and why are zeros at the bottom important?
It's because it's the you put it in the
little box in the left corner.
like right there.
It's what you can't have, otherwise known as, maybe I heard you say it a while ago, the domain problem. It's the domain problem. You guys were trying to be all spiffy, sorry. Just the domain problem. In the sense of the original said, hey, x can't be 2/3. So when we divide away, the denominator is gone, but we still need to maintain, the domain doesn't include 2/3. If you remember from Algebra 2, that's called a whole, because it removes, it's a removable discontinuity. Don't worry, we'll get back to it. Number 30, synthetic division. They don't show it as nicely as I do. I don't know, I like my box better than their, thing, but whatever. Either way, the -6 went in the box, final answer, you see it. Did it go in evenly? It had a remainder of, and how do we properly write it? As a fraction, yeah. Uh-oh. Why is it on this one? I think it's weird not doing homework. I'm like, oh, I should do a spot check. Come on. As a fraction. Number next one. Hey, it goes in evenly, which means the denominator is gone, which means we have to be like, ooh, the denominator looks gone. But x still can't equal 9 because it didn't equal 9 in the beginning. We're maintaining kind of the integrity of the problem, the meaning of the problem. Saying, oh yeah, we can rewrite this as something easier, but x still can't be 9, even though we divided the denominator away. Couple more seconds. Number 60 you can already see. Remainder 0. Goes in perfectly. This one asks you to find all the zeros which come from all the factors which we get because when we do synthetic division with -4, we have that x plus 4. And we have what's left, and that's just a quadratic. Easy cheesy, we got that. And just in case if you were like, what on earth? What is he doing there? Remember, this comes from the division it comes from the division, and we move the x plus 4 to the other side. So we did this division, we got this answer. If you're trying to look at the factors, the x plus 4 can go up, and we're like, oh, hey, look, it's the factors, and then the quadratic can go and be factored one more time, and then we set each one equal to 0. Dun, 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 dun. Did anybody have any questions on any of the odds? Awesome. 17. Anybody else? 57? Anybody else? Caleb. We can say 81. I'm sure someone somewhere else would agree. Anything else? We're good? Do you guys remember last homework what I said we were going to start doing with odd questions that people, not odd as in irregular, but odd as in, you know what I mean. Do you remember what I said we'd start doing?
Oh, that's right.
What was it?
You read the name of the hat. Someone's going to volunteer to go.
Yeah, keep volunteering for the boards and then comes your participation points. What? Oh, JJ's ready? JJ, which one do you want?
Number 17.
17, it's yours. Come on up.
Wait, can you describe what you're doing?
In the moment, no, but I might, if someone is still confused, have you talk it out once you sit down so it's not quite as intimidating.
Wow.
I'm going to go ahead and pause the video. So I'm not going to record you guys. Question. Y is... Y is the square root of -1. Alright. That's good. That's good. Just go back in notes. Hold on. Okay. Why is the square root of -1 a problem?
It's not a good number.
Okay, it's not a real number. It's imaginary. There's a negative. Why is a negative a problem? Because the one. But why can't a negative be under a square root?
Because in some way they multiply each other to get a negative.
Because. I don't know I'm about to confiscate any spirals in homework and books. But thank you for helping each other. Remember, speak the truth in love. That's biblical. Okay, so in order to take a square root, a number by itself, multiplied by itself, has to equal. And that's what I heard a lot of you trying to say. And what can two same numbers never multiply to be? Negative. Because a positive times a positive is a, and a negative times a negative is a. And the only way to get a negative is to have opposite signs. Which, if they're opposite signs, they're not the same number. Hence the dilemma. And hence why, basically, we can't deal with the square root of -1 as a normal, or I should say, as a real number. But we can define it, and we do define it, not just we, but the mathematical community, as I, as an imaginary number. And perhaps I'll be able to show you, not fully explain why there's such things as imaginary numbers, but at least demonstrate a little bit tomorrow. But for right now, let's just work with the basics of imaginary numbers. Now, first of all, an imaginary number is a number that has something to do with the square root of a negative. Okay? However, there is such a thing as a complex number that has, as you guys have already written, an imaginary component, hence the part with an I, right? And he's just on his own. He doesn't have an I. Oh. He's just a real number. Complex number is the sum of the difference of a real number and an imaginary number. So it could be something like 2 plus 3i or 2 minus 7i. And we'll look and see and make sure we understand where that comes from. However, there is a slight dilemma. If we have something like just an a to be like, oh, that's not complex. Actually, any real number can be written in complex form, just the v would be 0. And any imaginary number can be written as a complex number as well, with a real component, just the real component would be 0. So, technically, way back in the day when you guys were talking about all the different classifications of numbers, you don't necessarily have to write this down. I think this is what used to be in our old Algebra 1 book that you guys, if you were here in Algebra 1, would have used. There was like a chart sort of thing. And the chart sort of thing looks something like this. And the very inside they had the natural numbers. We should do the first one. The natural numbers, which are 1, 2, 3. Beyond that were whole numbers, which really just adds 0. Beyond that, do you remember? Were integers, which added negative counting numbers. Beyond that were rationals. I'm going to actually write that one because there are 2 R's. Rationals, which include fractions. And then beyond that were real, which included funny things like irrationals like pi or e or what else would you have done? Square root of 7. Like nasty things that can't be written as fractions. And then over here, totally separate, would have been imaginary. All the things with eyes. But here's the funny thing. You might not have known, but there's actually an overarching one that includes both. Any real number can be written as a complex, any imaginary can be written as a complex, and a complex has real and imaginary pieces. Interesting. Anyway, so, I can actually get to hit the right spot. Too far. Before we get to this page, wait. Do you hear me say that? I actually want to make sure that we have the idea of how to form or how to properly write an imaginary number. So let me just give you a couple examples, just real quick. We have the basics of where imaginaries come from, in a sense of, what if I was to say, write in standard form, standard, the following, let's just do two. Let's do three. And that means the standard form of a complex number. Let me start with something kind of basic like the square root of negative 121. Then let's go just a little bit harder to negative 32. Then let's go just a little bit more. Something like if we're writing it in the standard form, technically of a complex number. That's the section we're in, that's the context of what we're doing. Number 1. What do you guys think? Y11I. We could split this up into, you can think about it that way. And then we could say I11. Ugh, that's awkward, right? We put the coefficient in front. 11I. So any negative number that's an easy square root, no big deal. Take the square root and then add an I. But number 2, oh, this gets interesting. Huh? What do we do with 32? No, I don't want to do that. Oh, but we could do that. And put the I and we'd approximate by rounding. Take out a 4? Oh, hey, isn't that that thing where we factor and see any perfect pairs? Perfect squares? No! Come on, stop being a party pooper. So, if we go ahead and have a 4 and have an 8, we should have known that. Multiplication facts, right? 4 is 2 and 2. 8 is 4 and 2. 2 and 2. Although, maybe. Some of you guys see these 4s and you're like, hey, they're perfect squares. Or you could see that there are 2 perfect pairs and a leftover 2. There are many different ways of seeing it. Long story short, we could rewrite this as the square root of negative 1, because we have him. The square root of, I'm going to keep the 4s because they're kind of easy. We could split them up. Some of you guys are like, hey, it's 16 and 2. Okay, square root of 16 and square root of 2. Either way. Square root of 4 is 2. Just 2, no root. Square root of 4 is 2. Square root of 2, he's stuck. And then we have an I at the end. If we were to write it nicely, 4 root 2 times I. Just make sure your root doesn't coincide, or I should say your I doesn't crash into your root. He's supposed to be outside. I usually, if you guys are wondering, I usually put a little tail at the end just to kind of close in the 2 and say nobody else. But that's the proper way to write it because coefficients are in front. But you could have done, if you would have liked 4I root 2 as well, same meaning. Same meaning. All right, number 3. Exactly. We have the real. There is no imaginary, but we can still write it as a complex number. We got it? Good. Now let's keep going. Okay, so let's do stuff with the complex numbers. Let's start really hard. Let's add and subtract complex numbers. Why are you kind of laughing at me? Maybe it was time.
It wasn't me.
It was something. Someone did a quick little.
I was just trying to
That was Lucas. It was Lucas. Lucas.
Why is it funny? I agree, kind of. In the sense that it could be hard, but it's not, because all we need to do is what I write. Reals go with reals, imaginaries go with imaginaries. We just combine stuff. And watch out for poor little seals that might get trampled in the process. So, or something else. I don't know. Trampled is usually getting to death. So, what do I do with all those parentheses? Why? I do. What's like in front? Is it just like a 1? Distribute a positive 1 and everything stays the same. This for a few of you that might accidentally take them away and make it times or something weird. Not unheard of, but weird. What happens with the other one? Addition of, they stay the same. I still have a 5, and addition of a negative 4i, which is still minus. Then I say, hey, cool beans, 7 and 5 makes, and then 3i minus 4i makes 10 to 110. Cool. You know 5-year-olds can do algebra? How can they do it? You tell them, what's 5 apples plus 2 apples, and they say, hopefully, if they kind of know addition, how many apples? 7. 7 what? Apples. And you say, cool, take 2 giraffes plus 5 giraffes, and hopefully they can say 7 giraffes. Maybe you should do smaller numbers. Then you say, okay, cool, 2x plus 5x, and they'll say what?
7 giraffes.
Hopefully not. That'd be a very sassy little 5-year-old. So, 2x plus a 5x, what are they going to say? They're just going to say 7x, because the labels stay the same, right? Same thing here. 3i can only go with negative 4i. That's all that makes sense. And 7 plus 5 is 12. Keep going. There are just a few of you, and it could be your Achilles heel, a bad habit that might accidentally want to do 10i. That's why I brought that up. Some people would accidentally want to do that. Just their brain naturally goes that way. There's some sort of lack of foundation, and that's okay. It happens. But just remember, combine the terms. How do we do the next one, though? Not killing the seal. Distribute the negative. Not to the first one. He just stays the same. Imagine it's positive 1 time. That's all good. But the second one, minus 5 plus 3i. Just a few of you are like, psh, I would never make that mistake. Let's hope not. They're taught long enough to see that mistake over and over in my pre-calc and calculus AB and calculus BC classes. As you get higher, usually the easier stuff gets harder because you don't pay as much attention when mistakes happen. Don't text and drive. Okay, so now what? Negative 2 plus group of like terms, and you're done. Can you make that 5i?
No.
Or k? It's not an I. It's like adding apples and oranges and saying they're. I don't even think it is. Exactly. Now, what happens with multiplying? Foil! Don't kill a puppy. See it? Help yourself out. True? See it? Help yourself out. And then go. How many of you guys have learned how to distribute or multiply binomials with the acronym FOIL? Wow. The other way is just distribute one term to each of the other 2 terms, and then do the same thing with. If you want to, you can have fun and you can make a little like and say, yay, good job. Anyway, however you do it, whether a smiley face, whether a FOIL, you have to distribute each of the terms to the other. Do you see his nose? But first, we should get to where we can just do it in our heads and see a 16, right? Outer. What do you see? 8i. Inner. 8i. Last. Woo! So question, how come I'm gonna say, sweet, good job guys, 12 plus 16i and we're done?
I don't know, we can't do that.
This is the right answer. That's what Calc Chat would say.
Yeah,
So you use that improperly.
4i squared can go with the 8.
You can use it, just use it right. Tyler, you're saying, but wait, isn't the I squared something? You're right. Who is the I squared? Wait.
Squared is 1.
Ah, how do you know for sure? I squared is I times I. And who did we just say I is?
Negative 1.
Not improper.
It's negative 1.
Oh, gosh.
That's another calculator, great.
Yeah,
That's a good one. Also, good exploration. What happens if the square root squared? Who is I squared? Negative 1. I squared, imaginary squared, is real. That's rough. So then we would say, it is weird, right? 16 plus, add the i's together, 16i plus 4 times substitute. 16 minus 4 is 12, and there's my 16i. Now, last year, did you have some sort of weird table of all the different powers of i's that would be equal?
Yeah.
And you just like randomly memorized it, and now it'll just pop out? Okay. But, does this make sense? If you know who I is, you can break down any power of I into what it equals. But yet, it still might benefit us to quickly review the powers of I. But, I like saying, hey, just memorize it and hopefully it'll come back when you need it. I'd rather you understand it a bit more. Who is I? Square root of negative 1. My ones who are distracted, this is important. Just kidding, it's all important focus. Okay, so. I know, it's going to look weird for the first one. I is the square root of negative 1, which is I. It's true. I squared is, stop, it's weird on the first one, it'll make sense on the others. Square root of negative 1 squared. Can I do that? If you don't like that, I'll write it a different way. It means the exact same thing. Square root of negative 1 squared. Is that better? Square root squared cancels, and we get, what am I going to write? Stink. I started with blue. That's going to be too many colors. I'm going to get lost. Now it looks ugly. Stop judging. Okay. I cubed. Square root of negative 1 cubed. How about I squared times I? And I squared is who? Oh, so it's negative 1 times I. And negative 1 times I is? We could put in square roots, but it's a lot easier to think about it in terms of I. Hence why we said, who is I, and just went back to I. Who is I squared? Well, we use the square root of negative 1 squared just to remember, oh hey. But now we can just start using the building blocks that we've had from the first two steps. So for I to the 4th, what can we do? Why not? And I squared times I squared. Negative 1 times negative 1 is positive 1. Oh, struggle. Nose he was red, sorry. Hence, do you see how I'm doing little curlies at the bottom of my eyes? I to the 5th. Okay, that could be I times I times I times, no, let's not do that. I squared times I squared times I, how about I to the 4th times I? Does that sound good?
Yeah.
No?
Yeah, it does. I said, oh.
Oh, got it. So I to the 4th is just 1, and 1 times I is? Stink, do you see that 35? This is going to be rough. Keep going. I to the 6th. I to the 4th times I squared. Or I could do I to the 4th times I times I.
So that'd be negative 1.
I times I times I times I.
Negative
I
1.
squared times I squared times I squared. This one's easier. Why? Who's I to the 4th?
Positive 1.
Just 1. So then I can just say, oh, 1 times I squared, and who's I squared? Negative 1. So 1 times negative 1 is just negative 1. T's, how do you go to T's? Struggle. That handwriting thing. I to the 7th. I to the 4th times I cubed. You guys put it together. Who is he? Negative I. 1 times who's I cubed. It keeps on seeming like I'm going back to the one that's right before on the other side, right? I think that's a thing. And then last but not least, I to the 8th is I to the 4th times I to the 4th. And who is, what is, I know I personify everything, we'll see in a second. What is I to the 4th times I to the 4th? True? Question. Why is this pattern true? Because the pattern of what powers of I simplify to B repeats every what? 4. So if we can take a huge number and break it down into multiples of 4 and figure out how many additional i's there are, we can place it in the correct spot of, in a sense, the table. That we could memorize, but I hope we don't have to. So let me go ahead and model it for 1, and then let's see if you guys can repeat it for a harder one. 35. We're going to make a table all the way to 35. We're going to ask ourselves the question, how many 4s are in 35? Well, hold on, pause, just so we have the idea of what's going on. Some of you can mental math it, some of you not so much. How many 4s are there? 8. How many i's will be left over? Okay, wait. How many I to the 4ths are there? 8. Wait. There are 32 i's right there, right? Power to a power you multiply. So I have I to the 4th, 8 different pairs of I to the 4th. So I have 32 i's, and how many i's are left? 5 cubed. What can you do with any I to the 4th? It's 1. And 1 to any power is still 1. So all I have to do is break it down and say, oh, hey, it's the same guy as I cubed. If I were to make my table all the way to 35, he would fall in the I cubed line. And all the I cubed simplify to be negative I. Huh. So then you guys repeat the process with I to the 129. Go. Repeat the process with I to the 129.
Does this have to only be like multiples of 4?
Yes. Because remember, the pattern repeats every 4. I mean, we could break it down to 2s, but then you'd have to plug in a negative 1. Plug in.
I did I7 and I5 and I got the same.
But then wouldn't you have to figure out who I7 and I5? So you'd have to memorize this much of the table instead. You know what I mean? That's why I like I to the 4. He's basic. How about 128?
Oh, 128. I forgot. I to the 1 and 120. I got it.
Because,
I got I.
did you guys figure out how many times 4 goes into 129? For those of you that are like, how on earth did they? 129. Divided by 4, 4 goes into 12 3 times. I have the 12 taken away. I have the 9 2 times. How many i's are left over?
No.
So, 32 times 4 makes 128, and I have 1 I. Oh. What happens to that whole shabam?
Cancels out.
That's 1. 1 to any power is 1. 1 times I is I. Maybe it makes more sense because it's explained differently. Maybe it's just your brain needed another times the end. Do we have it? Okay. Does it make sense now? Why I'm doing this then? So I, if there's multiplication and there are higher powers of I, we should never leave them because they can always break down into either a real number like -1 or 1 or a power, I shouldn't say a power, lo siento. Either I or -I. So any multiplication can always be broken down, substituted in, and simplified to still be in the A plus BI form. There's one operation we haven't looked at, and it's division. We've done addition. Similarly, we've done subtraction. We've done multiplication. Talked about what if you get i's to higher powers. Our last thing is division. We're not reviewing dividing complex numbers. We're just reviewing what does it mean to multiply by 1 creatively. And our review is going to be common. We can do this. Common denominators or rationalizing. If we had something like 1/2 plus 1/3 without a calculator, cheaters. Making us dependent. How do we put those two together? How do we make a common denominator? There's no equation. We don't have another side. We're stuck to what we have. We have to keep it the same. We can't throw it off. So I really want to make them into 6's, right? 6. But what I do to the bottom, I have to do to the top. Why? 3/3 is the same as anything times 1 is its sum. So I'm not changing anything as to what it equals. I'm just changing what it looks like for my own purposes. Not usually healthy in life, but in math it's good. So coming over here, I would do the same thing to him and keep going. That's the common denominator example of how to multiply by 1 creatively. 2/2 and 3/3, they both equal 1, but I use them for a very specific reason. Question. One more example of when you multiply by 1 creatively in the past. When you solve or simplify and you get something like this. We say, uh-oh, who's not allowed to be proper? Who's not allowed to be in the denominator? A square root. And how do we get rid of a square root? Multiply by? Because what happens with a square root squared? A square root squared, the square root cancels, he's no longer there. What happens with I squared? Becomes -1, the I is now gone. So if we're dividing, proper form says you don't leave poor little i's in the denominator the same way we didn't leave square roots in the denominator. And how do we fix it? We say, hey, I squared isn't the problem. So we multiply top and bottom. It's just an I. Well, yeah, because look, on top we get 5i, on bottom we have I squared. And we say, oh, I squared is the same thing as a -1. And we just take the coefficients or the numbers and we can say 5 divided by -1 is -5. I don't have to lead on this 5/I. That's sad. And improper. Now what if, back in the day, you had gotten something like this? Would a square root of 2 suffice? Yay! Boo hiss. It would have worked great when I distributed to one, but when I distribute to the other, isn't there still a square root? The root 2 over root 2 would not suffice, and hopefully, even though you might not remember it, you learn something like, whenever there is a binomial with a root, we have to multiply by something called the, I almost rewrote it, the conjugate. And the conjugate says, take what's there, oh dear, change the sign in the middle. Don't you dare kill your seals, keep your parentheses intact. You multiply by the conjugate, because when you multiply by a conjugate, that's a difference of squares. You have first your outer and your inner cancel, and last, it's quite nice, the square root is gone. Now some of you might have to follow that, but let me show you how it applies in this case. I have an addition or subtraction. I have a complex number, real and imaginary. I'm going to multiply by 1 plus 2i over 1 plus 2i. Remember, just the denominator is my problem. So I multiply by his conjugate. Some of you are not going to like my next step, but long story short, I'm doing a lot of foiling. And my foiling would get me 6 at the end of the day, minus 5i minus 14i squared, all over 1 minus 4i squared. What happens to all my I squareds? They go to negative 1. So I have 6 minus 5i minus 14 times negative 1, all over 1 minus 4 times negative 1. This is something I can simplify. 6 plus 14, wait, 20. All over 5. Add some negatives, changing to positives. And oh my goodness, I can go one step more because I can pull a 5 out and factor. We'll make sure you're not killing anything on that tomorrow. But I end up with 2, 4, done. Homework Monday. Bye guys, have a good day. Hang in there. Finish this week off.
Sorry, Mrs. D. I was having a hard time with polynomial logarithms.